In this video, we will explain how we can use confidence interval estimation to perform statistical inferences. More specifically, we will compare and contrast point estimates with interval estimates and construct confidence intervals for population means and population proportions. We will also introduce t-distribution, another important statistical distribution. Let's look at the point estimates and interval estimates first. Example: the business school dean claims that the average weekly income of the graduates of her school 1 year after graduation is $600. The standard deviation is assumed to be $120. We draw a random sample of 36 students whose average weekly income is only $530. This question is related to the distribution of the sample mean. From one of the earlier videos, we have talked about that the sampling distribution of the sample mean is normally distributed with a mean of $600, the same as the population mean. And the standard deviation of this sampling distribution is the population standard deviation divided by sample size. That's 120 divided by square root of 36. That's 20. In summary, the sample weekly income is normal with a mean of $600 and a standard deviation of $20. Question 1. Does your sample support a dean's claim? Let's take a look at a sample mean of 530. It would be very difficult to gauge the size of 530 in the absolute sense. We know it is less than $600 because we have both the mean, which is $600, and the spread, which is $20 of the normal distribution. We can convert the 530 into a z-score. That's negative 3.5. This is a very small z-score. From the empirical rule, you probably remember that it's very unlikely to be less than negative 3 z-score. That means if the true weekly income is $600, it's very unlikely to get a sample average income of $530. Therefore, the sample does not support a dean's claim. Question 2. What would be a good estimate of this population mean income? The sample average is 530, so a natural way to estimate the population average income is to use the sample average, which is 530. This estimate is actually supported by central limit theorem, because the CLT says that most sample means are in the neighborhood of the true population mean mu. So we can estimate the population average using the sample average, which would be $530. $530 is one single valued estimate for the population parameter. It's also known as the point estimate. If we want to estimate a population parameter, the point estimate would just be the corresponding sample statistic. The point estimate for the population mean is the sample mean. The point estimate for population standard deviation is the sample standard deviation. Similarly, the point estimate for population proportion is the sample proportion. Can we do better than the point estimate? Yes, this would be the confidence interval estimate. Let's take a look. We also know that, according to the central limit theorem, there is about 95% chance that a sample mean is within about 2 standard errors of the population mean. To be more precise, it's 1.96. An interval estimate of the population mean would be an interval that is centered at a point estimate, 530, plus minus about 2 standard errors. That's about 39.2 here. It's an interval estimate between 530 minus 39.2 and 530 plus 39.2. I will explain how we could construct this kind of interval in the next few slides. As you can see, this interval estimate provides more information about the population parameter than the point estimate. It provides more uncertainty estimates. The width of the interval is related to a term that is known as MOE, which is also known as margin of error. The general form of confidence interval estimate is the point estimate plus minus the margin of error. The margin of error provides information about how close the point estimate to the value of the population parameter. If the interval is wide, we know that we are more uncertain about our point estimate. If the interval is narrow, we are more certain about our point estimate. As you see in our previous example, the point estimate is always going to be 530 because that's the sample average from our sample of 36 students. But the width of this interval can be different. For example, MOE, margin of error, could be 39.2 or 33. The width of the intervals depends on several factors. One of them is related to the confidence level. The confidence level is a probability that represents how confident we are with the interval estimate. The definition and interpretation of the confidence interval is the following. If the 95% confidence interval estimate for the population average salary is $500 and $560, it means that there is 95% probability for the true population mean to be between $500 and $560. An alternative definition of the 95% confidence interval is that we are 95% confident the true population average is between 500 and 560. Because we would prefer to be confident with our interval estimates, the commonly used confidence levels are 90%, 95%, and 99%. We are never 100% confident with our interval estimates, as that would mean the interval would be as wide as the entire real line, and that's not going to be meaningful at all. Next, we will talk about the exact form for the confidence interval of population means, followed by that of population proportions. There are two different formulas for the population mean, depending on whether the population standard deviation sigma is given or not given to us. If it is known, we use the formula on the left. The point estimate is the sample mean, or x bar. The margin of error, MOE, is a product of two things. The first is a z-multiplier, and the second is a standard error of the sample mean. The z-multiplier is a z-score that can be calculated using either Excel or z-table and depends on the confidence level. On the other hand, if the population is not given to us, we use the formula on the right. The point estimate is the sample mean again, x bar. The margin of error is also a product of two things. The first is a t-multiplier, and the second is the standard error of the sample mean. A t-multiplier is a t-score obtained from either Excel or a t-table, very much like the z-multiplier. Instead of using population standard deviation in the numerator of the standard error, we would have to use the sample standard deviation. As you probably remember, the population standard deviation sigma is not given to us for this situation. Let's take a look at how to find a z-multiplier or a z-score next. This depends on the confidence level. Say the confidence level is 95%. The z-multiplier is the z-score that has a middle area of 95%. Only the middle area is 95%. If the middle area is 95%, the two tails should add up to 5%. Each tail should be 2.5%. Z-multiplier has a right area of a 2.5% or 0.025. We can use Excel function to find a z-score given the right area to be 0.025. The function is nom.inf. For more information on how to use Excel to find either the z-score or probability, click on the video linked in the upper right corner of this screen. We first convert the right area of 0.025 to a left area of 0.975 by subtracting from 1. Z-scores are from the z-distribution, which is a standard normal distribution, not any normal distribution. There's an infinite number of unique normal distributions out there, characterized by different means and different standard deviations, but only one of the normal distributions is called a standard normal distribution, also known as the z-distribution. The standard normal distribution has a mean 0 and a standard deviation of 1. We input these two values using Excel nom.inf. Using nom.inf, we were able to find a z-score should be 1.96. That also means the z-multiplier is 1.96. You shouldn't be too surprised because we know from the empirical rule that 95% of the observations are within 2 standard deviations from the mean, and 1.96 is indeed very close to 2. After obtaining the z-multiplier 1.96, we can plug all these numbers into our confidence interval formula and obtain 530 plus minus 1.96 times 120 divided by the square root of 36. At the very end, the interval would be between 190.8 and 569.2. We are 95% confident the true population average weekly income of this school should be between $491 and $569, which is actually much lower than the $600 claimed by the dean. We can also compute the confidence intervals at other confidence levels, say 68%, 90%, or 99%. The steps are identical to what we have just described earlier. Please pause the video and see whether you are able to calculate the z-multipliers at these different confidence levels and construct the interval estimates. One thing I like to point out is, as the confidence level increases, say from 68% to 99%, the z-multiplier also increases, as you can see here. Consequently, the margin of error would also increase. You may recall that the margin of error directly determines how wide the intervals is. This implies that holding everything else constant, to achieve a higher confidence level from 68% to 99%, we would have to have a wider confidence interval. Let's take a look at this example here. Please pause the video and read the text on the very top. This question is somewhat different from what we have seen before, as we do not know the population standard deviation. So we cannot plug it into the formula with the population standard deviation. Instead, we use the sample standard deviation of 20 minutes. We plug 20 into the numerator and divide it by the square root of 15 to calculate the standard error of 5.164. The price to pay for this approximation is to use a t-multiplier instead of a z-multiplier. The t-multipliers are from t-distribution, so let's talk about the t-distributions next. A t-distribution shares many similarities with the standard normal distribution, also known as the z-distribution. It is also symmetric, bell-shaped curve, centered at 0. While there's only one z-distribution or one z-curve, there are many t-curves, many t-distributions. Each t-distribution is characterized by its corresponding degrees of freedom, which is usually written as a d.f. Degrees of freedom is this quantity that's sample size minus 1. Note that degrees of freedom here is always an integer. This plot shows the relationship between z-distribution and different t-distributions. The curves on the very top is the z-distribution. the normal distribution. It is very close to the t-distribution with a degrees of freedom 100 degrees of freedom, but quite far from the t-distribution with smaller degrees of freedom, say 1 degrees of freedom or 5 degrees of freedom. As the degrees of freedom of the t-distribution increases, the t-distribution becomes more like the z-distribution. If you're interested in learning more about the t-distribution, please check out the videos linked in the upper right corner of this screen. The steps of finding t-multipliers are very similar to that of finding z-multiplier because those two distributions are very similar to each other. In Excel, we use t.in function to find a t-multiplier. The first argument is the left area. At a 95% confidence level, the middle area is 95%. So the right tail is 2.5% or 0.025. The left area to the left of the t-multiplier here should be 1 minus 0.025, that's 0.975, so we put it here. The second argument, and also the last argument, is the degrees of freedom, that's sample size minus 1. It is 15 minus 1 in our example, so that's 14 here. After we input all of this argument into our Excel, we obtain a t-multiplier of a 2.145 from Excel. This is bigger than 1.96, you probably remember, the z-multiplier we obtained earlier. This suggests that when we do not know the population standard deviation, the multiplier increases, so the interval becomes wider, implying we become less certain with our point estimate of 530. In this slide and next, I will summarize how we can use Excel functions to solve probability questions related to t-distribution. The functions are t.dist and t.inf on the next slide. They are very similar to norm.dist and norm.in functions. See the video linked in the upper right corner. t.dist is useful when we know the values of x, when we have it here, and try to figure out the area to the left of x, or maybe to the right of x, as we have seen here. When we find the area to the right of x, we could also use t.dist.rt instead of 1 minus t.dist. Here is t.in function that's very helpful when we know the area to the left or to the right of a particular x, and we try to figure out what x is. Here is the same example we discussed earlier in this video. At a 95% confidence level, the multiplier is 1.96, and that's actually reduced to 1.645 when we reduce the confidence level to 90%. If all the information we have is the sample standard deviation, then we would have to use a t-multiplier for the confidence interval. Be sure to pause this video here to see whether you are able to obtain the same t-multiplier as me. Next, let's see how we can estimate confidence interval for population proportions. Similar to the confidence interval estimate for the population mean, the formula for the population proportion can also be split into two parts, the point estimate and the margin of error. The point estimate is the sample proportion, that is p bar. The margin of error again is a product of two things, a z-multiplier from a z-distribution and the standard of error. The standard error is a square root of p bar, the sample proportion, times 1 minus p bar divided by sample size. It is worth noting that we always use a z-multiplier for population proportion confidence interval estimate. In this example, we want to estimate the population proportion for purchasing a new phone. The point estimate is 16 over 100, that's 0.16. We just talked about the formula for the confidence interval estimate earlier, so you can see a point estimate p bar plus minus a z-multiplier times the standard error. To calculate the standard error, we would need to use population proportion p here. Unfortunately, we do not know p. We would approximate p using p bar instead. the sample proportion, and 0.16 in this particular example. Plugging all the numbers into this formula, we obtained the standard error, sigma p bar, is 0.0367. At 95% confidence level, we can calculate the confidence interval estimate to be 0.16 plus minus 1.96 multiplied by 0.0367. That's between about 8.81% to 23.19%. Please pause the video here to see whether you are able to calculate the confidence interval estimates at other confidence levels. There are more practice problems posted on our course site. I also highly recommend you to watch other teaching videos or walkthrough videos I've created for confidence interval estimation problems. Please feel free to check out these videos linked here. This also concludes the video, and I will see you in the next one.